In this problem, you've been asked to first find the cooling constant K for this equation where T is temp, capital T is temp, and lowercase t is time. And they've given us some initial conditions, 100 degrees removed from the oven. So that means 100 will equal 30 plus 70 E to the K times 0. Well, it turns out this makes total sense. We haven't really solved for anything. This is just proving that our equation is true, because 100 equals 30 plus 70 times e to the 0, which will be 1. But then it says, placed in a 30-degree kitchen, and after 5 minutes, the temperature is 80 degrees. So now we have another piece of information we can use. Instead of time is 0, time is 5 minutes. And instead of 100 degrees, we've gone down to 80 degrees. So now we have an equation we can solve. We're looking for K. K is the only thing we don't know. So we're going to try to get e to the 5K by itself. The first thing I will do is subtract 30. So we're looking at 50 equals 70 e to the 5K, or K times 5. And now I'll divide by 70. So e to the 5K equals 5/7. And you can turn that into a decimal, or you can just leave it. We're trying to undo this e, and we'll do that by taking the natural log of both sides. Ln of 5/7 will equal ln of e to the 5K. Well, this is an exponent, and one of our log rules allows us to bring that down. So we really have 5K equals ln of 5/7, or K equals ln of 5/7 divided by 5. As a decimal, that turns out to be negative 0.0673. The negative makes sense because we're cooling, or our exponential function is decaying. So now we'll attempt to answer number 1. What is the temperature of the object after 20 minutes? Well, we know temperature will equal 30 plus 70 e to the K, but now I know K. It's this negative 0.0673 times 20. I can plug this in my calculator, or I can do it in the graph, because we might need the graph later. So I'm going to pause and show you how to do that. So the first thing I've done is I've plugged the equation, just like you see, into my graphing calculator. Now I'm going to go to my window and set up my window as an ask, so that I can go to my table and start to see what kind of values make sense. At 0, I'm at 100 degrees. 1, I'm 95. 2, I'm 91. 300 was already in here, but it makes no sense. We're going to go 5 minutes. We're going to go 20 minutes. We're going to go 120 minutes, which would be 2 hours. And now you can see at 120 minutes, I'm almost down to the room temperature of 30 degrees. So this looks like a good window. From 0 to 120 in the X, and from 0 to 100 in the Y. So I'll go to my window. From 0 to 2 hours, or 120 minutes. And then the Y, we said we're going to go from 0 to 110 degrees. Now I'll graph it. Sure enough, it looks just like we thought. And we were asked to find the temperature of the object after 20 minutes. Well, if I go second, trace, I can calculate a value. And the value I want is at 20 minutes, because that's the independent variable t, or x. So 48.219 is my temperature. 48.219 degrees C. And then we'll look at the next question. When will the temperature of the object be 35 degrees? Well, now I'm going to go back to my calculator. 30 degrees was my asymptote. So I'm going to go in and for Y1, I'm going to put 35 degrees. And now I can see it's right here. This is the time that I'll be at 35 degrees. I'm going to go back to second trace. And this time I'm going to calculate an intersection number 5. First curve, enter. Second curve, enter. I don't need a guess, but if I wanted, I could get close to the intersection point. Hit enter. And now we know at 39.213 minutes. Just round that to 39.2 minutes. That's when we'll be at 35 degrees. Now we could have done this all using algebra, but in this case the graphing calculator can work much faster since you've already set it up.